Case study, Adapting to Cyber Threats, a comprehensive AI-driven approach for enhanced cybersecurity at Cybertech Solutions. Cyber threat intelligence has become indispensable in the digital age, where cyber threats evolve at an unprecedented pace. At Cybertech Solutions, a prominent cybersecurity firm, AI-driven cyber threat intelligence has been integrated to bolster their defense mechanisms. The team, spearheaded by Dr. Emily Carter, a leading cybersecurity expert, and her lead data scientist, Michael Turner, aims to explore and utilize the latest advancements in AI to stay ahead of adversaries. The team initiates their project by examining the efficacy of supervised learning models in identifying known cyber threats. They train a decision tree model using a labeled dataset containing historical network traffic data. The decision tree rapidly classifies incoming traffic as benign or malicious, achieving a high accuracy rate. But can supervised learning suffice in an environment where new threats emerge daily? Michael raises this concern, prompting the team to consider other techniques that could address this challenge. Dr. Carter suggests exploring unsupervised learning models to detect anomalies indicative of novel threats. They deploy a k-means clustering algorithm on unlabeled network traffic data, aiming to identify patterns and outliers. Surprisingly, the algorithm successfully detects multiple instances of zero-day malware. However, how can the team ensure that the anomalies identified genuinely represent malicious activities and not just harmless deviations? This question sparks a debate among the team members, leading them to consider the integration of additional verification steps. The dynamic nature of cyber threats necessitates adaptive defense mechanisms. Reinforcement learning emerges as a promising technique. The team designs an automated intrusion detection system that learns from ongoing network activities. The IDS agent receives rewards for correctly identifying threats and penalties for false positives. Over time, the system improves its detection capabilities, adapting to new threat patterns. Yet, Dr. Carter questions whether reinforcement learning could inadvertently learn and perpetuate biases present in the training data. This consideration prompts the team to incorporate mechanisms to regularly update and diversify the training dataset. Deep learning, a subset of machine learning, further enhances their capabilities. The team experiments with convolutional neural networks to analyze visual malware signatures and recurrent neural networks to scrutinize sequential network traffic data. The CNNs demonstrate remarkable accuracy in identifying malware based on image patterns, while the RNNs effectively detect anomalies over time. However, how do these complex models balance performance with interpretability? Can cybersecurity analysts trust and understand the decisions made by these models? Michael proposes using interpretability techniques like LIME and SHAP to make the decision-making process more transparent. Natural language processing becomes a focal point when the team investigates the vast amount of unstructured data available on forums, social media, and darknet sites. By employing named entity recognition, they extract valuable insights, identifying IP addresses, domain names, and emerging threats. For instance, an NER algorithm flags a forum discussion about a new malware variant, allowing the team to take preemptive measures. Yet, how can they ensure the reliability and relevance of information extracted from such diverse sources? Dr. Carter emphasizes the importance of cross-referencing data from multiple sources to validate findings. Graph theory proves instrumental in mapping the relationships between various cyber entities. The team constructs a knowledge graph to illustrate the connections between IP addresses, domains, and malware samples. This approach helps them uncover interconnected threats and predict future variants. A knowledge graph reveals that several malware families share commonalities, aiding in the development of targeted defense strategies. Nonetheless, can this approach scale efficiently as the volume of data grows? Michael suggests leveraging graph databases and parallel processing to manage and query large-scale graphs efficiently. Anomaly detection techniques like isolation forests and autoencoders add another layer of defense. The team deploys an isolation forest algorithm to partition network traffic data, isolating potential anomalies. Concurrently, autoencoders compress the data to identify any deviations by measuring reconstruction errors. These methods uncover previously unknown threats, significantly enhancing their detection capabilities. But how can they mitigate the risk of false positives that might overwhelm security analysts? Dr. Carter proposes integrating a feedback loop where analysts can label false positives, refining the algorithms over time. Threat intelligence sharing and collaboration with other organizations become a key strategy. The team adopts the MITRE ATT&CK framework, which provides a comprehensive database of adversary tactics and techniques. This shared knowledge base enables them to understand and anticipate attacks more effectively. By using standardized formats like STIX and TAXII, they facilitate the automated and structured exchange of threat intelligence data. However, what measures can ensure the confidentiality and integrity of shared intelligence? They decide to implement encryption and access controls to safeguard the shared data. Despite their advancements, the team faces challenges. Adversaries continually evolve their tactics to evade detection, often using adversarial machine learning techniques to fool AI models. Michael notes that attackers could generate adversarial examples designed to mislead their models. To counteract this, they incorporate adversarial training, exposing their models to both normal and adversarial examples to fortify their robustness. How can they maintain the balance between robustness and performance? Regular evaluations and fine-tuning of models become essential to achieving this balance. The interpretability of AI models remains a critical aspect. While deep neural networks offer high accuracy, their black box nature makes it difficult to explain their decisions. The team implements LIME and SHAP to gain insights into the decision-making processes of their models. By doing so, they can provide explanations for AI-driven decisions, increasing the trust and confidence of cybersecurity analysts. However, how can these interpretability techniques be integrated seamlessly into their workflow? Michael devises a user-friendly interface that visualizes the explanations, making it easier for analysts to interpret and act upon them. In conclusion, Cybertech Solutions exemplifies the integration of theoretical models and techniques in AI-driven cyber threat intelligence. By leveraging supervised, unsupervised, and reinforcement learning, deep learning, natural language processing, graph theory, and anomaly detection, they enhance their ability to detect, analyze, and mitigate cyber threats. Threat intelligence sharing and collaboration further amplify their defensive capabilities. Addressing challenges such as adversarial tactics and model interpretability ensures the robustness and reliability of their AI systems. Through continuous innovation and adaptation, they remain at the forefront of cybersecurity, safeguarding digital assets against evolving cyber threats.